We have one more talk before the coffee break, and that's Professor Uri Weiser, who is a now emeritus professor at Technion, and he's our next speaker.
You want to use this one? Let's try this one. Do you need a pointer? Yeah. Yes, okay. And the pointer is in the middle.
Okay.
And the pointer is in the middle. Yeah.
Wonderful. Okay, thank you, Carlo, and Yale for inviting me to Stamatis Symposium. Actually, Yale tried to convince me to come to this conference for a while, and I couldn't come. Last year I came, and I was really excited about the informal environment that exists here, and I love the conference. Thank you. So I'll talk. This is an example of the concept that we are working, and the concept is talking about the different or new environment that exists, which is big data, and where would you prefer to execute your program? So, looking in general. Big data is everywhere, we understand that. The computing environment or resources are not being used very efficiently, and definitely heterogeneous approach is the right one. If we look at the application range, we all know that whatever you put here on the vertical axis, it is performance or efficiency. Definitely, if you narrow the application range, you can get better performance or efficiency, and that means that actually using, for example, accelerator, and when you talk about accelerator, it's not only the hardware itself, but where the hardware resides. So this is really application dependent. But if you look also at programs, there's a lot of time dependent, meaning along the time this X, which may be performance or anything else, is really changing along time. This, by the way, 1.5 is 15 seconds for one of the programs we are looking at, and we see the difference in behavior along time, and difference in behavior along time usually requires different approach by the hardware itself. So what are the implications? And we'll try to follow that. So the first question, so we decided to approach this direction of heterogeneous computing by using one example, and the example that we took is where to process and when to process in storage. So the first question, it is why to process in storage, and the second should be when actually to process in storage. So let's try to look at it. So the message is actually to build a tool that actually will tell you or will identify where, when, and how data should be processed. And in our example, we look, shall the data be processed at the storage, or at the host? You know, somebody else can ask, is it the right place, the memory is the right place to process the storage or not? So let's look at first of all, about the environment. And when we look at the environment and try to understand big data, we see what we call a lot of read-once. Read-once is actually data that being accessed to memory only once along the program. And the example that we did here we took samples of 10 million instructions and tried to find what are the unique addresses. And we look, how many times you access each unique address. And if you look at GNU grep, you see that there's a lot of read ones, right? And, to other addresses, there are some accesses, the unique addresses, but there are some accesses, but they are consume much less bandwidth than the read ones. So the read ones is a major issue when we talk about big data, and we have huge amount of data, and you want to access all the data. In order to be efficient in general, you have to read it once, otherwise it will take you forever. So the read once is a non-temporal locality memory access. And by the way, we know that our system that we built till now actually is built for temporal locality. We talk about registers, we talk about caches, we talk about DRAM, are all built for temporal locality. So what we did, we said, okay, let's look now at the program parameters. So if there are cases of read once, let's try to identify them, but it's important. It's not only the read once element, but how many times along the time axis you reach data in general. So this is the data intensity. Data intensity said, how many bytes per instruction are being asked by the program, and we talk about memory bytes. So in general, when you look at your program, you can understand how many bytes per instruction, average instruction you access, and we call it the MPI. The other is the locality factor. The locality factor is actually algorithm-based, and actually it said, we call it alpha. It's the byte to storage versus byte to memory. How many cases, from all the memory accesses are actually accesses to storage? We can understand that if the alpha is 1, that means for every access to memory, there's actually access to storage. So the read once, our case of read once, the alpha will be 1. So what we decided to do, usually in our case, we try to access any problem with analytical model first to understand, well, what are the rules of the game. So what we did, we look at, this is the case where you process in host. So you have the cause and you process the data in host. And another option is to process the data in storage. By the way, this is the simple, really simple equation, analytical equation that says what is the instruction per second that exists. This is the alpha that I was talking about. And the main problem, by the way, that we look when we talk about read once is the bandwidth limitation of accessing to storage. And we want to see what will happen in cases of big data if we'll reach this bandwidth limitation. So first of all, what we did with this simple equation, we said, okay, let's look what is the bandwidth, right? Out of the instruction per second, you can identify what is the bandwidth requirement. And we said, what is the bandwidth requirement versus the byte per instruction, the average byte to memory per instruction, and as a function also of alpha. And of course, you are getting the minute you have alpha, which is 1, meaning there's a lot of read ones, you get quite a lot of requirement in the bandwidth. And of course, if the byte per instruction is high, meaning you access a lot of the memory, you have this speed. But what happens if the bandwidth to the storage is limited? Then you cap the access to memory, and this is the case of limited bandwidth. But if you have a limited bandwidth, we wanted to see by the equation only, we actually find out that the performance is dropping. Of course, whenever you access memory or storage, and you access the limit of the bandwidth, the implication of the fall in performance is dramatic. And this is what we see here. So we saw it. I like, when the student came with this graph, I said, very nice. Let's see if it's true or not. So what the student did, we took we created a synthetic benchmark that changed the byte pair instruction and changed also the read ones percentage. So in this case, all the access to memory are read ones, and here only 1% of them are read ones. And we measure on a real system, and we got suddenly this drop, very similar to our analytical model. At this point, I say, wait, it cannot be. Right? With this so simple analytical model, you're getting something that you can validate on a real system. And then we found out that actually what happened, so we thought about it, then we found out the drop here is so dramatic. It's, 1 to 10 or even more. It's order of magnitude drop in performance that, all the rest, the operating system and the caches and the system itself in general are all changing the performance in 10% or 20% or 30%, while the bandwidths actually hit you in order of magnitude. And because of that, when you go to a real system, you really see it. Okay? So then it's simple. The minute we got the red one, we said, yeah, if we process in storage, right, then in case that the process in host will fall into this dip, it's better to process in storage. And here we try to emulate the process in storage. In this case, there's no limit in bandwidth, and then you get this graph, and then you say, okay, fine. Now we can understand when, it's the right time to process in storage. So this is the case that we did. There's just a foil regarding the energy analytical model. Of course, that in case that you are in the dip of the bandwidth, the energy consumption will be dramatically up, and we checked it on real system also, and we got very similar results. So let's look at the program behavior, and we took several applications, and these are the applications, and actually we measure the real alpha, meaning how many read ones you have in this program versus the temporal locality accesses, and in grep and BLTN and so on, the alpha is pretty large. In sort, of course, in two phases of the sort, in one phase, the alpha is pretty small because you're looking at the data several times in order to sort it. But in the second phase, it's growing. If you look at the byte pair instruction, the interesting result that we got that the word count have a very poor byte pair instruction, and because of that, although the alpha is pretty high, you still don't reach the drop in the performance. So, but what is interesting about these two elements that we are identifying, the alpha is algorithmic based. So you look at the algorithm and say, how many times do I have to access this data? It's part of the algorithm. While the BMPI is very dependent on the software efficiency base. If you use SIMD, single instruction multiple data, probably the BMPI will go up, right? It really depends on your compiler. If it's a good compiler, probably you'll have less instructions meaning that the BMPI will be high. So these are the two elements. So what we did also, as one of the professors that we showed it, he said, the three-dimensional, it's very hard for me to comprehend. Let's go for two-dimensional. So what we did, we do a contour plot, and the contour plot is lines with a constant performance, and for this line example, level C, LZ4, you see that this area is the plateau, right? And here there's a drop in performance, and this borderline is the borderline of the edge of this hole in performance that you get. What we did we draw it for LZ, and we draw the specific LZ that we have. And by the way, it's very interesting because the X line is actually the measured one, and this is the calculate. So, the difference between the calculate and the measure by the simple analytical model is not far away. So this is for LZ. The BLTN is outside of this drop in performance, so don't, process it at storage. Definitely for LZ, process in storage. The graph, for sure, you see the drop. Here's the drop in the performance, in the whole, and actually the program itself sits very well, or reach the bandwidth, the limited bandwidth there, and because of that suffer in performance, and so on and so on. Of course, in general, what we are saying, definitely there are some programs that's better for them to perform in storage, because if not, they will reach the bandwidth limitation, and that will cause really a deep performance drop. So this is again the example that we did on real system. We emulated, and actually we are seeing in those cases that there are many cases that you can get quite a performance improvement whenever this application actually reaching the bandwidth limit. So you can see you can get 2x and 3x in performance very easily to some of the program. And this is the message that we are having. The message is, first of all, our systems are not totally efficient across all applications. And definitely when environment change and you have new application, look at the cases in which those applications are not fitted to the current system that exists. And try to look at the big issues, not the small one, not the 10% or 20% in performance, although it's important, but there are a lot of cases that in the new environment, there is big issues in our current system. And the case that we look is that, we look at the bandwidth, and we found out that yes, there are many cases in which the location of the performance or the computation should be elsewhere, not in the host. Thank you.
Thank you, Uri.